Okay, guys, today I'm going to talk about the first depth map creating software I wrote. That was some time ago. So if you go on my website, so 3dstereophoto.blogspot.com, go to software tab and you go down. Okay, so that's the first one I did, this one. It's called DMAG, so Depth Map Automatic Generator. Just DMAG with no number. So if you click on that, and here it explains the thing. So it's very math intensive, and that's why I liked it. So here I said that the algorithm is based upon this. So let's look at it. Yeah, variational methods. Okay, so here I explain variational methods, variational methods, and I show basically it's an energy, so it's a sum over all the pixels. Okay, so the energy is dependent on so UV is the displacement. So this is in the context of optical flow. So optical flow means that you are interested in the displacements of objects or pixels from one image to another. So that's why you have a UV, which is displacement field. XY is the position, so that would be like the pixels. XY defines the pixel location. UX, UY is the derivative of the U, and VX, VY is the derivative of the V, the displacement in the Y direction. So U is the displacement in the X direction, V is the displacement in the Y direction. Okay, so then I say, oh, you solve this thing to minimize that energy and use Euler-Lagrange equations. Is this, so it's just derivatives. Okay, so then I look into okay, so here I'm actually looking at the equation for the optical flow stereo matching. Yeah, so here, okay. So I'm just going to show how do you get the energy. So the energy is the sum, so the sum is over all pixels in your image. So I2 is the, let's say you have two images and you transform them into grayscale, then it means that I1 and I2 are the intensities. Okay, so it's varying between 0 and 255, 0 being black, 255 being white. So it's the grayscale value. So I1, it's on the, if you're looking at the stereo matching, that would be the left image, and I2 would be the right image. So this is called the data term. So you for matching, you want the intensity to be the same on both images. So basically, when you do stereo matching, you want to figure out when you look at the pixel on the left image, where is it on the right image? So assuming that you have figured out where that pixel went, then the difference between the two intensities should be 0, should be minimum. That's why you're trying to express in this equation, if you will. It's in this term, I should say, in this term of the energy, the data term. So you want this I2 minus I1 to be as small as possible. So on the I2 term, which is basically the right image, it's X plus U, Y plus V, where U and V are the displacements. if you have just a stereo matching, the V would be 0 and the U would be the disparity, okay, or the depth. And then you have another term, which is the smoothness term. So there's going to be a weight attached to it so that you can control it in the input parameter. And it's so the gradient of U square plus the gradient of V square. So what does that mean to be smooth? It means that neighboring pixel should be at the same, should have the same displacement or the same disparity if you're talking about a depth map. But this is more general because it doesn't assume that the two images are aligned. Here you could have images not aligned. That's why you have the U term and the V term. U term, V term, which is the optical flow. So smoothness, you want this term to be small. Okay, you don't want neighboring pixel to have different displacement or different disparities. Okay, so here I'm expressing I2. So this is a Taylor expansion when with I2 being dependent on two variables, okay, the U and the V, and then you have to assume. So this is Taylor expansion, but it's assuming UV is small. So that means the displacement is assumed to be small. So then, okay, so now you have the expression for the energy, and you want to, so you use those equation, the Euler-Lagrange, to solve that. Okay, so that's your equation. It's actually, once you have them, it's pretty simple. Then it means that at each pixel, I explained that here, at each pixel xy, you therefore have two equations. And the derivatives, you can evaluate them using finite differences. Okay. Here I explain what it means in like a physical sense in one dimension. So that's pretty intense in terms of mathematics, but at least it explains how you get there. Okay, so let's forget about this one. Let's look at the, okay, so this is done. So DMAG is an implementation of the algorithm described in blah, blah, blah. It's by, the main author is Thomas Brooks. And you will see or hear his name a lot when you do optical flow. But I'm not going to go through the papers. There are two papers you can look at. So then I show some examples. And this is something I actually do not recommend to get depth maps. I'm showing this just for like researchers, so that they don't have to reinvent the wheel. Because as of maybe 2 weeks ago, I started putting my code into GitHub. Okay, so I'm just going to show you. Let's get out of here and just show you GitHub, because I started putting my stuff on GitHub so that people can use the code I wrote and do their own thing, their own research. So okay, so I'll put a link to that repo in the info box of the video, so you can check it out. So it's all there. You can just clone the thing and do your own thing. And it's I did this in Linux, so it's very geared towards Linux, but I think you could probably compile and link this stuff in Windows. But I mean, I don't really know how to do it, so somebody else is going to have to do it if they want to. Okay, so now let's continue. Okay, so those are just examples. Okay, and then, so what I did is that I wrote like a PDF that explains how to use DMAG, in particular the input file. So let's have a look at that. Okay, so this is the document. Okay, so again, it's gonna show that this energy formula, which is basically kind of the same, but not quite as the one I showed before. The only difference is here. So W is the displacement vector, so that's the UV, the UV displacement. Okay. So this is annoying. Let me see if I can get rid of this. I don't know if I can. Okay, so let's look at this quickly. The energy, so this is the same as before. So you have the I x plus W minus I. So here it's the I. This I is the I of the, like the right image, or the, yeah, the right image should be the I of the left image. Here you have a gamma, which controls the amount of, so this is the smoothing. No, it's not smoothing. This is, okay, here what I do, here I look at the intensity. Here I look at the derivatives. Instead of looking at the intensity directly, I look at the derivatives. Why would you want to look at the derivatives instead of the intensity? It's because of sometimes between the left image and the right image, there is a difference in illumination. So you don't get the same intensity even though the points are supposed to match. So often in depth map calculation, you always see like a gradient term along the intensity term. So it's just an add-on. You don't really need it, but it's actually very useful. So those two terms are data terms. And this is the smoothness term. Okay? So this enables you to get smooth depth maps at the end. If you don't have this term, you're going to get a lot of noise. Plus, I think the solution is not unique, so you may, I don't think it's even going to work if you don't have a smoothness term. Okay, so here I explain so that energy, the functional. Okay, and then here I explain the parameters in the input file. So the name of the input file is DMAG _ input.txt. So these are the items in that file. So you have image 1, image 2, factor. So this is the downsampling factor. For that, I'm gonna have to use my drawing tablet to explain that. Number of scales. Epsilon, we don't really care. That's just a stabilization term. Gamma, that's quite important. I mean, relatively important. This is the weight you give to the gradient matching cost. Okay, so if you go back, okay, so this term, which is part of the data term, so here you have the intensity matching, and this is the gradient matching. So this is the gradient, the cost related to the gradient matching cost, it's called. So usually you put alpha at 0.9, that's a good value, or the gamma at 0.9, sorry. And alpha, okay, so alpha is the weight of the smoothness term. So this is very important. The higher the alpha, the more smooth your depth map is going to be. The lower the alpha, the less smooth, but probably the more accurate, okay, the depth map is going to be. And then you have several parameters here that don't really matter that much. Okay, and then you have your, so this is going to be a disparity map in the U direction and the disparity map in the V direction. Of course, this one you don't care about if you do stereo matchings. You only care about this one. And those are normalized. Okay. So here I explain how I derive the equations. This is the Taylor expansion. So it's linearization. So you're assuming small displacement. You assume that the displacement vector is small. Okay, so here I'm explaining everything in that document actually. But let's look. And then you have the results. Okay. So the results, they're okay. I mean, it's an interesting method. But you can see that sometimes also it depends on the alpha value, the smoothness weight. But I mean, you get interesting stuff. So it's not something I would recommend to get depth maps. And also the advantage of this is that you don't need to give the minimum and maximum disparity. This thing figures it out automatically. So that's a plus. Okay, so let me see if I can explain further. So basically you have one image. So this is image 1. And you have image 2, image 2. So if you're doing stereo, it's going to be left image, right image. So in this image, you have so usually this is Y and this is X. Okay, so you start from the top left corner. So this is XY, so this is pixel XY. Okay, and so this is the same one, so same XY, but this pixel may be over there now on image 2. So maybe this is the head of somebody, and this head of that head has moved here in this has moved from here to there. So this vector, here is the UV, and in the PDF I call it W, and it's in bold. It's in bold because it's a vector. Okay, so this is the displacement, and that's what optical flow is all about. You want to figure out the value of that displacement. How does this object on image 1 ends up here? What's the displacement value? So when you do stereo, let's say you have I don't know, something here, and it moves here basically. Like it was here and now it's here. So in stereo that would be just the U, and you would call it disparity. Okay, you would call it disparity. So that kind of explain the terms used. Okay, so now what you do is that, so this is your image, and this is also true for the other one. So let's say this is image 1. What you do is that you're going to create a pyramid of images by reducing the size. Like let's say you reduce by this amount and then you reduce by this amount, and then you reduce by this amount. Okay, so that's called like a pyramid of images. So for instance, in the DMAG, there's a parameter that controls by how much the pyramid of images shrink at each scale. So this would be scale, I think it's 0. This is scale 1, this is scale 2, this is scale 3, and the amount, like I read here, I might reduce by 25% in each direction. Okay, and this is I think it's called factor. So here in this case it would be 0.75. I think it's the default I use. So why do you do that? Well, you don't have a choice, you have to. And it's because if you look at the initial image, okay, so this is your image 1 and this is your image 2. So for stereo, that would be your left, that would be your right. So let's say you have some object, and this object moves by this amount. Okay, so it was here. So it moved by this amount, which is quite large. So that's the displacement. Okay, so what happens if you reduce the size? Okay, so this is the same. This is this image. So this is the reduced version of image 1, and this is the reduced version of image 2. And if you look at this object, so now it's much smaller. So here it's here. But the displacement, so now it's moved to maybe here. The displacement, so the UV, so here you had the displacement, you had the UV. So let's call it U0, V0, and this is going to be like UN, Vn. So n is the scale, at which scale you are. So you have scale 0, which is the original size, scale 1, scale 2, scale 3, scale 4, and it gets smaller and smaller. So this UN, Vn, very small. And why is it important? Is because you can, if the displacement is very small, you can linearize that energy term. Okay, that's what I showed in the on my website. Because it's small, I can linearize using Taylor expansion. So that's the whole idea. So what you do is that you can figure out the UN, Vn at that scale. So this is scale n. Scale n. This is scale 0. And of course, in between, you have scale 1, 2, 3, n minus 1. Okay, so there's a bunch of scales here. Okay, so you can compute the UN, Vn at scale n, and you use this solution as your starting point for the scale before that. So scale n minus 1. Okay, and again, you can linearize because the displacement is going to be small. So at scale n-1, you get a solution, and you use that solution as the starting point for the next scale. And you keep doing that until you reach scale 0. And at the end, you get your U0, V0, which is the final, which is your final solution. In our case, we don't care about the V0. We only care about the U0, and the U0 gives you your disparity map, or aka your depth map. Okay, so I think I'm gonna stop here. Yeah, I made this video primarily because I wanted to show that my code is now on GitHub. I mean, not everything, I just do it piece by piece. So right now only DMAG is on GitHub, but I'm gonna, you know, as I have time, I'm gonna put the repo. I'm gonna put repos for each software that I've ever produced on GitHub. So the next one will probably be a DMAG 2, then DMAG, I don't know, DMAG 3, I might not do it, DMAG 4, DMAG 5, etc., etc., etc. Okay, so I think I'm gonna stop here. If you have any questions, feel free to put them in a comment. Please like, comment, subscribe, and I will make more of those. And I'm very sorry about my drawing skills, but it's not that simple. And by the way, this video is made on Linux using OBS, and I use shortcut to actually make the movie, the actual video. So OBS is just to record the screen. All right, I'll see you around. Bye.